let's look at acceleration versus time for this example of a not moving car. And hopefully this one's not too crazy, because if an object's not moving and it has no velocity, then it is also not accelerating. And we showed last time that the slope of the velocity was the acceleration, which was 0. So remember, acceleration is the change in velocity. It's changing velocity. And here, since the velocity is not changing, we're not going to have an acceleration. So we can, we'll note that there's no change in velocity, and then we'll go ahead and note our points. So our acceleration is 0 meters per second squared. We'll put these dots along. So each point is telling us at every increment of time, this thing is still not accelerating. So now on the acceleration versus time, it's telling us the acceleration at a given time. So the acceleration here is 0 meters per second at all time periods. And what does the slope mean? The slope then, rise over run. The rise is meters per second squared over the run of seconds. So that means every second is the object's acceleration changing. So is the acceleration changing? And in this case, it is not, because it's not moving. So we're mainly going to deal with constant acceleration. I'm not going to do any examples that are changing acceleration. So for us, we're usually not going to use the slope data. But if you're doing physics that requires changing acceleration, which isn't super uncommon, you would need to be able to understand the changing acceleration and the slopes of those accelerations. Okay, area, again, base times height. So now we have seconds times meters per second squared. One of those seconds will cancel, so you're left with meters per second, which is velocity. So the area is going to tell you the velocity. And I think I forgot to note this, but it's not just the velocity, it's the change in velocity. So it's going to tell you the change in velocity at a given time interval. So it tells the velocity at the time interval, and not just the velocity, it tells you the change in velocity at the given time interval. So I apologize, I forgot to note that down there, but that is a really important point. I think I note it on some of our next examples. So area under the curve is 0, and so and again, base times height, 4 seconds times the height of 0, 4 times 0 is 0, so 0 meters per second. That change in velocity is 0 meters per second. All right, so now let's go to one where now we have, I think we'll do our positive acceleration first. We got our upward slope in displacement, our horizontal slope in velocity, and so now we have our velocity is moving towards the right. So velocity is moving to the right, and it's moving at constant velocity here. So now let's look at what that looks like in acceleration versus time. So a positive 1 meter per second velocity, what's that look like for acceleration? All right, we'll get our axis. So x-axis, still time. Y-axis now in meters per second squared. And a point tells the acceleration at a given time. And each point is telling us the acceleration now. And the slope is the rise over the run. So the rise is in meters per second. The run is in seconds. So that's meters per second cubed. Is the acceleration changing is what that is telling us. And here, no, the acceleration is not changing. So horizontal line on a acceleration time graph tells us there's no acceleration change that's taking place. And the area underneath, if you do the base times the height, so base in seconds, height meters per second, is going to tell us meters per second. So that is giving us the change in velocity here. So is that object changing velocity? And this one, we'll see why change in velocity is important at later ones here. But the area is 0 meters per second. So all points are 0 meters per second squared. So it is not accelerating. So at no time along here is it accelerating. So there's no change in velocity. The important thing to note is just because there's no change in velocity doesn't mean that it's not moving, okay? Just because there's no change in velocity doesn't mean that it's not moving. It just means it's not changing velocity. That's why we need multiple graphs or multiple data points to really help us out. Good, so there's acceleration versus time for positive. Now let's look at negative. So now our car's moving backwards, and we see that it looks the same as the previous one because the acceleration is still 0. A point still tells us the acceleration is 0 at every single point along that curve, every single point along the line. It's not moving. All points are 0 meters per second. It's not accelerating here. So we're going to have a horizontal line. And the slope is the rise over the run. So the slope here, meters per second cubed, is the acceleration changing? And here, no, it's not. So we have no change in acceleration. And the area is telling us the change in velocity. This one, oh, I see a little error. It doesn't mean that it's not moving necessarily. It just means that it hasn't changed in velocity. So again, on both those, make a little note. I see that I made a little quick error when I was writing that the biggest thing to probably misconception that I see that I wrote down there, it's not that it's not moving, it's that there's no change in velocity. So now let's look at these last ones. I think I clarified that a little bit more here, that not moving versus just not changing velocity. So we have our little rocket dude who's falling, and he turns on his rocket here. And then he starts going upwards, the velocity starts going upwards, and the force of his rocket and the acceleration are all going upwards also. So again, he starts by falling downwards, and then the velocity changes once he gets to 0 and starts moving upwards. So recap, displacement versus time. He started with a big negative velocity and went to 0, and then he ends with a big positive velocity. So we had a positive acceleration. The velocity is changing. There is acceleration taking place. And so that negative velocity is becoming more and more positive over the entire time period here. And we saw the slopes get steeper and steeper and steeper. And the area still doesn't really mean much for us in displacement versus time. Now, velocity versus time with this one, remember we had an upward facing slope, which means we had a positive acceleration. And if we looked at these points and said they're A, C, and E to kind of line up with what's going on here, at A we had that big negative velocity. At C we had velocity of 0, so we were right in the center. We're at 0, velocity of 0. And then at point E we had a big positive velocity. So we got a big positive velocity there. So slope gives the acceleration that we have going on, and it's a positive slope, so that is going to be a positive acceleration. And you don't memorize that, you just remember that the units tell you what you have. So the units tell us that the rise over the run is meters per second squared, and we know that's acceleration. And then the area there, we'll fill in the positive part of the area. The area tells us the change in our displacement, our net displacement. So our net displacement here is 0 meters because it started at 10 meters, it goes to 0, and then it goes back on up to 10 meters. It has that positive displacement. So it has a negative displacement to start, and then a positive displacement at the end, the second half of the slope from 4 seconds to 8 seconds. So we end up with a positive we end up with the displacement of 0. And the whole time we have a positive acceleration because the slope is upwards. So let's look at the acceleration versus time graph here of what's going on. So acceleration versus time now of this graph. So acceleration versus time of this graph, again, we know we have here a positive acceleration. So the acceleration is positive. It's going to be on the top side of the graph. And our acceleration is in the same direction of the force. It's going upwards, even though at the beginning his velocity was going downwards. So a point along this curve tells us the acceleration at that given time. So at a given time, we know any particular acceleration when we look at the curve. And all our acceleration points are positive here. So that acceleration is going to be positive all the way across. And the area under the curve now, so our area here, this is going to tell us, when we plug in our units, we have base times height. Base units are seconds, height units in meters per second squared. Seconds, we get one of those that cancel, so meters per second is velocity. So that's going to tell us the change in velocity. So here we'll know the change in velocity over this time period. So let's make sure we make this quick note, because I didn't make it super clear up to this point, and I think one point I did tell you that the thing wasn't moving, and it was moving because it was a change in velocity. So let's clarify that. The velocity found from the area is the change in velocity. So you need to know the initial velocity to know the object's velocity at a given time. So it's really good to know what the object's initial velocity is, either on one of your other graphs or via another piece of data that is given to you in the problem. But you can't know the initial velocity just by looking at this graph here, okay? It's going to tell you the change in velocity. And the slope here is going to tell us rise over run. So we have meters per second squared over seconds. That's going to tell us, is the acceleration changing? So change in acceleration. And here we have a horizontal line, so the change in acceleration would be 0. So there's no change in acceleration. This guy has constant acceleration. So our acceleration is not changing. Horizontal line right there. And all points are equal, so acceleration is not changing. And our area, the area tells us the change in velocity. That's our big key. So acceleration graphs, area tells you the change in velocity. And here our acceleration was g. Now we have a negative acceleration. So we have our displacement time example here. You start out with that big velocity at the beginning when the ball is going upwards. By the time it reaches the top of the arc, it's moving 0. And then it has the big negative velocity by the time it gets back down. Right? So at the beginning here, we have a big velocity going upwards as it rises. And then by the time it got to the top, velocity stops. Acceleration and force of gravity are the only things acting on it. So velocity starts moving down. And those are our two graphs that we have so far. Let's move those to the side now. And let's draw what that looks like with acceleration versus time. So acceleration versus time for a negative acceleration. We have our time period here, 14 seconds. And accelerations in meters per second squared. And what does a point tell us? Point's going to tell us the acceleration at a given time when we're talking about acceleration versus time. And at all times, the force of gravity is going downwards. So the acceleration is also going to be pointing downwards due to gravity on this ball. So at all points, the acceleration is negative 9.8 meters per second squared, which is g. And that's from the force of gravity acting on that ball. And gravity always directed downward when we're looking at objects typically falling towards the earth here. And so the acceleration is constant at all times that it's about negative 10. So at all points, the acceleration is going to be negative 10 meters per second squared. And the slope's telling us the change in the acceleration. So is the acceleration changing? And no, it's going to be constant. The acceleration's not changing. It's a flat slope. Gravity is consistent here. The force of gravity is consistent. So we have negative 9.8 meters per second squared at all points along this curve, all points along the line. And our area is the change in velocity. So if our area is the change in velocity here, it's going to tell us the change in velocity up to a specific point in time. But again, our little reminder, we need to know that initial velocity to know the actual velocity at a given point. So that would be bonus data either from another graph you're given or info you're given in a problem. But you can only know the change in velocity up to a given time with the area under this curve. So the base times the height here, the base units are seconds, the height unit meters per second squared. And what does that tell us? It tells us meters per second, and when we calculate that, it's negative 140 meters per second. So over the time period, it has changed 140 meters per second in that time interval. There it is, folks. I hope that was useful for you. Hopefully you're able to hang in there and learn a little bit about slopes and graphs and points, really the big three: point, slope, and area under that graph. And just remember what those things mean. Remember the units, and you can figure it out and hopefully not have to memorize quite as much. But good job. I enjoyed being here with you. And let me know if there's anything I can do to make that a little clearer in the future.